we already know what is work. Okay, so suppose if I have a mass, okay, and I want to take this mass from point 1 to point 2, then certain amount of work has to be done, okay, if external field is present. Okay, so then this work for taking it from point 1 to point 2 will be given as integral of f bar dot ds bar. So f bar is the force and the ds bar is the infinitesimal displacement. So this integral will give me the work done. Note that when I was telling about the definition of work, I was telling about the work being non-zero only when external field is present. Okay, so what do I mean by that? Suppose if you have a point charge, okay, let's say plus q charge is there with you, and you want to take this plus q charge from point A to point B. Okay, if an external field is not there, that means the potential at A and potential at B both will be zero, because when there is no electric field, there is no potential. Okay, so that will mean that you don't have to do any work. Why? Because the work done, the electrostatic work done, will be given as Q VB minus VA. So this is the formula of electrostatic work. So VB minus VA is 0 because both are 0. So the 0 amount of work has to be done. But if you have an external electric field, okay, suppose in this direction, the external electric field is there, then the work done will not be 0. Why it will not be 0? Because the potential will not be same at point A and point B. The potential at point A will be less than the potential at point B. So why it is like that? Because electric field is given as the negative gradient of potential. So that means the direction of the electric field is nothing but the negative gradient of the potential. That is, the direction of the decrease of the potential will be the direction of electric field, right? So here the decrease of potential is towards left. Okay, so the potential at B will be higher than the potential at A. So now VB minus VA is some non-zero value, so the work done will be Q times VB minus VA. So this is the work done in the presence of electrostatic field. So now you have understood that in the presence of field only the work is done. Another example you can take is that of the gravitational potential. Okay, if I have to take a mass from ground, okay, to a certain height 10 meter, if I have to take this mass of 1 kg suppose from ground to 10 meter height, then I have to do the work of mgh. So what is mgh? M is 1 into g is 10 suppose into 10. So this is 100 joule. So 100 joule energy or 100 joule amount of work has to be done because of the presence of the gravitational field. Because of the gravitational field, there will be a difference in the potential at these points, this P and Q suppose. Okay, so now only in the presence of the respective potential field the work done will be there. Okay, if it is not there, then it is 0. For example, the gravitational field itself is not there, then there will be no question of potential at point Q and point P, so there will be no work done. So now we will look at it in detail. Okay, so I will again write the formula from 1 to 2. F bar dot ds bar is the work done. Okay, now I can apply the Newton's second law here. F bar, the total external force F bar, can be written as m dv bar by dt. So this is the Newton's second law. So I will write m dv bar by dt here into the dot with ds bar. So now I will assume that the mass is constant. That's why I took mass outside, because actually the force is equal to rate of change of momentum, right? And the momentum is, that is the linear momentum, is mv bar. So I am taking m outside of this because I am assuming that mass is constant. So this will be equal to m from 1 to 2 dv bar by dt dot ds bar. Now what is this? Suppose I have to write v bar in terms of ds bar. So this is ds bar by dt. Okay, so I have to write v bar in terms of ds bar. So I can write it like this: v bar dt is equal to ds bar. So sorry, I made the statement incorrectly. I want to express ds bar in terms of v bar. So now I can write ds bar as v bar dt. Okay, so I will write it here from 1 to 2 dv bar. Can I take this here? So if I take it here, ds bar by dt will become v bar. So here it is v bar dt. So it becomes from 1 to 2, mass m is there. So this is v bar dot dv bar. So I have expressed ds bar by dt as v bar. So now v bar dot dv bar from 1 to 2. So I can write it as v bar square, okay, from 1 to 2. The limits are from 1 to 2. So I can write it in a scalar form. So this is mv2 square by 2. Okay, so the integration will be, so we know that integration of any variable x dx, suppose, is x bar by x square by 2 plus c. So since there is this is a integration with the limits, I don't have to have this constant over here. So this is mv2 square by 2 divided by mv1 square by 2, sorry, minus mv1 square by 2. So this is nothing but half mv2 square minus half mv1 square. So this is nothing but the change in kinetic energy, because this quantity is given as kinetic energy of the mass.